Greetings and welcome, friends. Mr. Wada here. Today we are talking about two new types of special segments. Well, I guess maybe you're familiar with one of them anyway. Within triangles that will have some interesting outcomes. So check this out. First one is called a median of a triangle, and it is a segment that goes from a vertex of your triangle to the midpoint of the opposite side. I just want to point out it would not have been very interesting if it went to the midpoint of an adjacent side. That's just kind of not interesting. And so this is a median of a triangle. It connects the midpoint of the opposite side to the vertex. There are three of those within a triangle because there's three vertices within a triangle. And what's interesting is that the three medians are concurrent. Who saw that coming? What? That's so crazy. All three medians intersect with each other, and the point of concurrency is called the centroid. All right, the centroid is what we've got. Isaiah, you with me? Right? Good, good. So let me show you real quick. Let me select these sides. Let me construct some midpoints. Bam! You notice that? Look at that multitasking. And let's see. Let's construct. You can construct segments that way, but I like using the segment tool when possible. Bing, right? As long as I'm snapping. Snap, let it snap. Look at that. Oh, snap. And so there we go. Notice that these are, let's see. I missed it. Yeah, there we go. And no matter how I draw this, all three of those medians will be concurrent, and it's called the centroid. That is like the coolest name ever, right? Now, centroid doesn't have any cool circles that I can draw. Not really. But there are some interesting outcomes here regarding the ratio of where this lands with respect to the vertex and the side when traveling along the centroid. So let's see, if I find the measure of A to D and get that distance, and I find the measure of D to E and get that distance, I don't know if you can see anything interesting with those numbers. Yeah, it looks like that DE is half of A to D. If I also compare that to the entire median, measure distance, we will find that, let's see, let's do a calculate. Let's compare the vertex to the centroid, divide by the entire length of the median. You'll end up getting a ratio of 2/3 no matter where I go. So point D is 2/3 of the way along AE from the vertex, right, Jack? Yeah. So, question?
Always?
Always.
So you could just draw one and then know where point B is.
Yeah. So yeah, notice wherever I move this, it's always 0.67. All right. Or you could also say AD is twice as long as D to E, or vice versa, right? DE is half of AD, and that's true for whichever median I'm working with. Okay, so let's compare that to the entire length across. That's probably going to be an F there. Let's see, measure distance, and let's do number calculate, and let's compare this divided by that, and look at the same 2/3 ratio. The centroid is 2/3 of the way down the median from the vertex. Cool? All right. Cool. So let's use do an example. Actually, wait, I didn't finish reading this. Yeah, the medians of triangle ABC meet at point P, and AP is 2/3. AP is 2/3 of the entire length AE, BP, blah, blah, 2/3. Good. Let's do example 1 together, friends. Example 1, so you guys can follow along. Right, Aiden? You cool? Cool? All right. So, right, and once you know this little fact, it's kind of like easy to implement, right? It's just, 2/3 is kind of what you end up doing. So, it says in triangle RST, point Q is the centroid. Lovely. I love it. All right. And it says SQ is 8. It says find QW and SW. So let's see. I know that SQ will equal 2/3 of SW. All right. I happen to know SQ is 8. Question.
Couldn't you just say it's whatever half of the first number? Like
this length will be. I'm finding SW right now.
it's just
Yeah, you could have found that and then added them together. Yeah, a segment addition postulate, right? Yeah. Good times. I just want to point out like that the very specific formula will work, but I think that you guys will be able to do shorter routes. So let's see. SW is going to equal 3 halves of 8. 8 divided by 2 is 4. 4 times 3 is 12. So SW is 12, and Q dubs is going to be the remaining third of SW, and 1/3 of 12 is 4. Right? So not that bad, right? So that's 4, and the entire length is 12. Any questions? No. All right. Let's see about working with coordinate plane. All right. So here we go. Example dose. Find the coordinates of the centroid triangle RST with the given vertices. Now, I gave us a coordinate plane without a axis on it. It looks like all of these points are in the first quadrant. I anticipate that I'll be able to plot all my points in the first quadrant. And I think I gave us enough space. So let's see, over 2, up 1, R is right there. S is 5, 8, so 2, 4, 5, and then up 8, 3, and 3, and 2. There's my S. And T is at 8, 3, so 2, 4, 6, 8. Did I count that right? Yeah, and up 3. All right, so there is T. I will connect these dots. Connect the dots. La, 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 la. Right, good times. Drawing my triangles. Right, Alyssa's tracking this. Yep. All right, so there's our triangle. Now, if I want to find the medians, all right, and the coordinates of the centroid, now how do I find a median? It connects what points? It connects a middle. What's the math word for middle when I'm talking points? The midpoint, which the midpoint formula is the average of the x's and the average of the y's. So I should find the midpoint of 2 of these sides then, maybe?
wait, why is it the point? Did you not the point of like
Oh, you want to try to use the 2/3 thing? Yeah.
Wait, couldn't you do it the other way? Right.
Let's see. We could try the 2/3 thing. Yeah. What's your question, Anthony? You wanted to find 2 medians and then the intersection? Yeah. You could. I mean, both of them will be. Let's find the midpoint of RT. Because it looks like this might conveniently be a vertical line for that median. So let's see, RT midpoint. RT, so that's going to be 2 plus, all right, so 2 plus T's x coordinate is 8 divided by 2. The y coordinates 1 and 3 added together divided by 2, right? The average of the x's and the average of the y's, that is going to be 10 divided by 2 is 5. And 4 divided by 2 is 2. So over 5, 1, 2, 3, 4, 5, up 2. Oh, no, you didn't. Right there's our midpoint. And it happens to conveniently exist. The median ends up being a vertical line. Who would have thought? Thing of beauty right there. Right? So there's my median. So here's our median. Now, I could find the equation of that median. I could find the equation of another median, and do the intersections of the two. In this case, because this is a vertical line, it's actually not that bad. What is the overall length of this median? 1, 2, 3, 4, 5, 6. Let's give this a name. I don't know. They gave it V. So SV is going to equal, we could do this like super proper using the coordinates, but I think you can just count the boxes at 6. And the centroid is going to be how far along on this? 2/3 from the vertex. So let's figure out what is 2/3 of 6. So 6 divided by 3 is 2. 2 times 2 is 4. So that means from the vertex, I would want to move 4 units down. All right, 4 units down, and that is going to be my centroid. All right, so what are 4 y coordinates less than s? That's going to be which point? That's
1, 8, 1, 4.
Sorry. S was at 5, 8. What is 4 units below that? 5, 4. So our centroid is at 5, 4. In this case, because that ended up being a vertical line, that was pretty easy to work with. Also, the other centroids would have landed at fractional or decimal points. That would have been a little bit more of a pain to deal with. But I want to point out that, yeah, Anthony, you're right. We could have found 2 separate medians, found the equations for those medians, and find the intersection of those medians whenever it ends up being a little bit more complicated. All right, let's talk about altitudes. Are you celebrating the fact that Halloween is over and you can sing Christmas songs? Okay. So let's see, guys. Here we go. Altitude. An altitude of a triangle is the perpendicular segment from the vertex to the opposite side, or, gentlemen, or the line that contains the opposite side. When you have an acute triangle, your altitude will be in the interior of the triangle. But some of you guys with Geometry Sketchpad earlier, when you realized you had an obtuse triangle, your altitude was kind of like on the outside of it, and you'd had to extend one of your sides in order to get it. All right, so it says, yeah, it's perpendicular to one of the sides. You could think about altitude as the height of a triangle.
That's not wrong.
Oh no, that's a real altitude. This would be the height of triangle QPR, or one of the 3 heights.
How is altitude?
You can call it height.
Yeah, right.
All right, so let's take a look at Geometry Sketchpad again. Some of you guys didn't get as far on this one. So if I want to construct some altitudes, I can select a point and the opposite side, construct a perpendicular line, and notice, this altitude sometimes is outside of the triangle and sometimes not. So what I recommend is using your line tool, there we go, is extend the sides of our triangles and make lines out of them. Yeah, let me change some colors on these. Actually, that one's an altitude, isn't it? This one and this one. Let's see, display, line style. I'll make these dashed.
No, make the other one.
I'll make the altitudes dashed as well. Don't you fret. All right, so you can see that altitude goes from C to this intersection right here. That would be our altitude there. Okay. So here's an altitude. Let me change that color. Display. What's a good color? Green. Green. I heard a yay. And line style.
No. Don't make them dash. Make the triangle fixed.
No, it's fine. It's fine. So guys, here is one of my altitudes. Sometimes it's on the inside. Sometimes it's on the outside. Let's construct the other two altitudes. So A and its opposite side, construct. There's 3 altitudes in a triangle. Here, look at it. It's just, it goes from a vertex perpendicular to the opposite side.
Oh, so it's like 1, 2, 3. Oh, I get it.
And what's interesting is this is one of those ones where you can't have an altitudes intersect outside of the triangle. Now, what was the name of this special point of concurrency? This is the orthocenter.
The center has to be inside.
Yeah, centroid would have to be on the inside because it's 2/3 along the way. Yeah. But the orthocenter doesn't necessarily have to be. Yeah. So there we go. Thing of beauty. Let me hide this point. So that is called the orthocenter. The only interesting thing about this is that they end up, these 3 segments, these altitudes or heights, ended up being concurrent. There's not like a cool circle that I can draw from them. There's no cool like property that I can tell you about them really. There are, maybe someday, maybe during an ACE, you should investigate the relationships between these special intersections of special segments in a triangle. There's a relationship between all of them. Well, actually 3 of the 4, I believe, but I'll have you guys investigate that on your own. So let's see, the orthocenter, the location depends on the type of triangle. Could be on the inside whenever you have an acute triangle. When it's a right triangle, it'll actually land on the right triangle. And when it's an obtuse triangle, yeah, these colors, these pictures won't make as much sense in black and white. So the white outline border is the triangle, and it's possible to have the orthocenter on the outside. When I have, oh, I ended up hiding one of my points that I shouldn't have. Yeah, when I make an obtuse triangle, notice that the orthocenter is on the outside. Good? Let's do an example. Example. All right, there we go. Example 3. So guys, how do I construct orthocenters? Don't grind the gears there, Tyler.
By making altitude.
Altitudes. So that means I'm going to have to be aware of perpendicularity. That's a good one to know. And the other side, it doesn't necessarily pass through any points that's special on the opposite side. So let's connect some dots. So let's see, point X is at -5. 1, 2, 3, 4, 5, down 1. There's my point X. Y is at -2, up 4. Plotting my points. Ba la la la. And Z is at over 3, down 1. With the Z. And let's connect those dots. Yeah, so you guys are playing along at home. Don't grind the gears, Alyssa. You are destroying our construction tools. Yeah. Yeah. So there's our triangle. Tell you what, I'm going to zoom in on mine just so that you guys can see it a little bit better, as well as our folks at home. Gets a little bit more pixelated, but that's okay. Oh, that was like a miss, swing and a miss. I wanted to have it perfectly overlap this-ish. There we go, that's good enough. Bam. So there's my my triangle XYZ. It looks like this is an acute triangle, so I'm expecting all of these altitudes to be in the interior of this triangle. It says find the coordinates of the orthocenter, which altitude will be the easiest one to find?
Probably.
Yeah, the one that passes through y, right? It looks like that'll just be a perpendicular line. So I think we could even just draw that by I. So we've got one altitude right here. What is the equation of that altitude?
Y.
X equals -2. Actually, I'll write the equation. Yeah, so x equals -2 is the equation of this yellow line. I only drew the interior part of it, but that would represent the entire line. What do you guys want to shoot for, the x altitude or the y altitude?
Y.
Let's see. The book shot, or sorry, x or z altitude, my bad. Z? Okay, so I'm looking for a line that passes through z that is perpendicular to xy. How could I go about constructing that?
Draw a line.
I'm going to have to find the slope of xy. I heard some reminiscen of that. So the slope of xy, or I forget how I was labeling these things, slope of xy, looks like it's going up 2 over 1, up 2 over... no. No.
Just do XZ. Like the... Over 1, up 2, right? YZ would be...
Well, someone else made their selection. We could modify it if you're like, oh, that one looks like more work. Up 5 over 3, looks like. If I didn't know that from the graph, I could find the slope using the slope formula, subtracting their y's and putting that over the difference of their x's. So let's see, xy is what I'm working with, so 4 minus -1. And -2 minus -5. Right, change in y over the change in x. It's going to give us the same value. So 4 minus -1 is 5. -2 plus 5 is 3. That's the same slope that you guys were saying just a moment ago. So if that's the slope of xy, right, notice up 5 and over 3, that does confirm. What is the slope of my altitude through z going to be? I'll just call this z alt. I don't know. Zalt. So yeah, it's going to be the opposite reciprocal of that, so -3/5. And so that altitude has a slope of -3/5, and it passes through z. Now, if I wanted to do this graphically, let me show you a trick. -3/5 is the same as 3 over -5. You guys agree? That I'm doing the altitude that passes through z's slope is what I'm talking about. All right, I'm hoping, I'm rooting for this point right here, but I actually don't know. But using this slope, you actually could, with the graph, be like, aha, down 3 over 5, down 3 over 5, that's going off my graph, is the same as going up 3 and backwards 5.
Hey, wow.
And so that's like a super easy way that I conveniently had it work out for me. If I didn't see that, I could have used point z and the slope and found the equation of that line. Let's see, how are we doing for time? Yeah, I'll just verbally walk us through this. I could have found point z, all right, using point z in the slope. Plug that into slope-intercept form, gentlemen. Jack, Isaiah. Plug that into slope-intercept form. I could have found the b, then using my new equation and the equation of this one, find the intersection, which would have given me that. All right, so there's a lot of ways to do this. You guys are familiar with the algebra, so we'll spare ourselves that work so then we can get another example in here. All right.
I have to find 2 of you.
Yeah, because all 3 of them are going to be concurrent, so we might as well save ourselves some time. Right. Also, I do want to point out that the y-intercept here would have been ugly It would have been some weird decimal. You could have worked in point slope form, but I haven't showed you guys point slope form in a while either. What are the coordinates of that point?
That one.
-2, 2. Yeah, -2.
And what's the name of this point?
Ortho center.
Orthocenter. Orthocenter. Can I, what? Nothing. All right. Let's see. Let's do example 4 real quick. Take a look at it. See if we can at least outline this proof. Elmo's World is what Lauren was singing a moment ago. Oh, wow. I didn't know who the source was. Yeah, I didn't realize that. Patient 0. So here's example 4. It says, proving a property of isosceles triangles. Prove that the median from the vertex angle to the base of an isosceles triangle is an altitude. Okay, so if it's the median, that means it connects the vertex and what point? The midpoint of the opposite side. So that's why these two are congruent. Okay? So, given this, let's prove that it's an altitude. How do I prove it's an altitude? How am I going to prove that's an altitude, friends?
Prove the triangle. Side. Third. Yeah, side.
Oh dear.
Side, and then reflexive and
All right. Uh-oh. My mouse died, and now it's going crazy on me.
Yeah.
All right. So you guys are going to try to prove these triangles congruent first?
The jab angles congruent to the.
So all the given stuff is true, as usual. Someone was saying side, side, side. How do I do that?
BD is reflexive.
I like it.
Then they're congruent to side.
I like it. Let's see. So triangle, what do you want to call that? ABD and CBD. By side, side, side. I agree.
And then it's perpendicular because of the way it is. No, because D is ADA and BDC are linear pair. Is it linear pair adjacent angles? Something like that? I don't know. I think it's like.
Okay, so these are a linear pair.
Yeah, and that means that they're perpendicular because of the way it is.
Means the sucker is perpendicular.
Now, the reason that's true is given. Okay, Malik?
No, they're not.
All right, that these two are a linear pair. I also know they're congruent to each other.
Yeah, and they're right angles because it's not a straight angle.
So how do I know that angle ADB is congruent?
Yes.
You guys got it, right? So let's see. They're congruent. Don't pack up. Do not pack up. These are congruent to each other by CPCTC. And since they're a linear pair and they're congruent, they're going to add up to 180, and they're congruent. Their measures are equal by def of Kong. They're both going to be 90 degrees. I'll say, yeah, measure angle ADB is 90 degrees.
Woo!
All right, by linear pair postulate and some substitution there. And if those are 90 degrees, then those are right angles. And angle CDB are right. By def of right angles. I'm sorry. Let's see. And if those are right angles, then I could say that BD is an altitude, right?
Yes. Is there like a theorem for that?
Definition of altitude.
A theorem for
Def of altitude.
Control.
All right. Thank you for watching, internet friends. Have a great day.